Today's lesson, section 12.3b, we'll be discussing partial sums and infinite geometric series with our geometric sequences. So partial sum is similar to an arithmetic sequence that we had in 12.2. So for a geometric sequence of a sub n equals a times r to the n minus 1 power, the nth partial sum will look like a plus ar squared plus ar cubed all the way up to that a times r to the n minus 1 power. And so the formula, this one only has one formula, unlike the arithmetic one where you had two different ones. Here you just have one where it's a times r minus r, or like 1 minus r to the n power divided by 1 minus r. So we only have one option, so then we need to make sure that we know our first term, our common ratio, and what n is for our partial sum. So example 4 says they want us to find the partial sum of the geometric sequence that satisfied the given conditions. So here we have 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 all the way up to plus 1 over 256. So this is our nth term. We just need to figure out what term that is in the sequence. So if I look at my first point, my a value is 1, and then to look at my common ratio, I just need to divide here. It tells me it's geometric sequence, so I just need to do 1. So here, remember it's the second of the two that you're looking at, and then divided by the previous. So negative 1/2 divided by 1 would give us negative 1/2. If you need more confirmation, you can do 1/4 divided by negative 1/2. It'll get you negative 1/2 as well. So that'll be my common ratio. And so then from there, using the kind of the same thought process of before, use your equation. So the nth term will equal my a value. So here it's 1 times the r value, so negative 1/2 to the n minus 1 power. But this is equal to 1 over 256. So now I need to use my exponential solving abilities to get n out of the exponent. So here I'm going to take the log of both sides. Okay, so now I can move this down. Okay. Now when you're looking at this equation, if you remember from logs, all our log talk that we had in chapter 4, here I cannot have a negative 1/2 for the log. But if we look at the sequence, and just in this case, because you're going down by a constant 1/2, the pluses and the minus, the negative value part of it does not change the ratio at which it goes down. So if we just had all pluses, it would still go down by 1/2. It would just change the sign, really. So when I do this in my calculator, and this is the only time I'm ever going to do this, is I'm going to ignore the 1/2 that I have here when I divide those two numbers. So what I'll plug in is log of 1 over 256 divided by log of 1/2. Okay, so I'm ignoring the negative, just in this case, only because it doesn't really affect the common ratio. So I'll still get the same corrective value at the end, because it's positive as well, because for the 1 over 256, but it doesn't change what answer I'll get at the end. Okay, so when I plug that into my calculator, that value will equal 8. and then from there I need to add 1 to both sides, and so that gives me 9 as the term that represents 1 over 256. So then when I go back, now I'm still going to use the ratio of -1/2 when I do this. So for my partial sum for the 9th term, I do my a value, so it would be 1 times 1 minus -1/2 to the 9th power over 1 minus -1/2. Okay, and so now I want to simplify. So I don't need the 1 in front. And then the 9th, or -1/2 to the 9th power, is going to be -1 over 512, because 9's odd, so it keeps the negative. And then at the bottom I can change the sign, so 1 plus 1/2 gets me 3/2. And then I can do the same thing for the top. So now 1 plus 1 over 512, I can make common denominators, so 1 is the same thing as 512 over 512. So 512 plus 1 would get me 512 over, 513 over 512 divided by 3/2. So I want to multiply both sides by, or the top and bottom by 2/3, reciprocal, and then I could reduce. So 5/13 and 3 go into each other evenly, so the 3 makes it become 171, and then the 2 goes into the 512 evenly, so then that reduces it to 256. So you are left with that fraction, 171 over 256, and that would be your partial sum for this geometric sequence. Okay. Now the next thing we want to talk about is infinite series. Now we've been talking about just sequences. So sequences are ones that end. So they have a starting point and they have a finishing point. If we talk about an infinite series, just like the word infinite means, it goes on forever and ever to infinity. So you're going to the infinity of term. So if we look at an expression of the form of the sigma of a sub k from 1 to infinity, we're just going to continue going this way until we get to this number, but we'll never get to that number because we don't know what that number is. So we call these infinite series. Now, infinite series can have partial sums of two different things. You can either be convergent, meaning it converges or ends up becoming a number, or it can be divergent, meaning it never approaches an actual finite number. Okay? So if s sub n, so your partial sum, approaches a finite number as n approaches infinity, so as we continue to head towards infinity, then it's convergent. That means that it's going to eventually it's going to be a sum. So an example of this would be or just the thought of if you just took a half. So if you started with a whole and divided by 1/2 and divided by half again, so that gets you a fourth. Half again is 1/8. Now eventually that one you can keep going till infinity doing that, but actually the sum of that ends up heading towards 2. And so if you punch that into your calculator and actually looked at that one, in the book they have a good example of dividing up a piece of pie. And so they continue to cut it in half to show you all the sums that they're adding, all the terms. Ends up being 2, so it's actually heading towards a significant number. Now at the beginning it looks like it's just getting small, like 1, and then it's 1.5, then it's 1.75, then it's 1.875, and then it keeps getting closer. So it's almost like 1.99, 1.999, 1.99999, and so on and so forth. So eventually it should head up to 2. It's not going to be greater than 2, it's just going to be 2. Okay? So that's what I mean by convergent. Divergent would be like if you're taking, let's say, a series that's 2 to the nth power, let's say. So for that one, you'd start with 2 to the first, which is 2, plus 2 squared is 4, plus 2 cubed is 8. And you keep going up forever and ever. Now, those numbers continue to get bigger and bigger, so they're really not going to be approaching anything. You're just going to get a large, really large number at the end, so it's just going to head to infinity. So that's what we call divergent. So it's just not converging to some number. Now, we want to be able to apply this with geometric series. So the sum of a geometric series, so that would be if it has this form, instead of just the a sub k kind of thing. So if r, your common ratio, is less than 1, then the infinite geometric series looks like the following. So it goes from a plus ar plus a squared all the way up to infinity. So from 1 to infinity. That means it's going to converge because of the r value. So if it's got to be less than 1 for it to converge. If it's less than 1, then, and remember it's the absolute value of 1, so it's really in between -1 to 1. Okay? Now it's not going to be 0 in there because that won't make much sense, because we don't have, it's not really a geometric series if it's 0, but every other number in there would make sense. Okay? So it converges, and then it has a sum of this. Okay? Now that equation is derived from the previous geometric sequence's partial sum equation, where it's a times 1 minus r to the n power divided by 1 minus r. So what happens is in the top, because you're heading to infinity, r to the infinity power is going to be, since it's less than 1, it's going to be such a small number, it's eventually going to converge to actually being 0 when you plug it in, because it's such a because n, the power is so large that it makes the denominator so large that 1 over a very large number is just kind of basically 0. So then you get 1 minus 0, so it just becomes 1. Oh, whoops. So then the a that's out front just gets to move up top, so that's why you get the a in the numerator now instead of out front. And so then the bottom, because the bottom is not affected by the value of n, it just stays 1 minus r. Okay? So that's where they get that summation notation from, or sorry, the partial sum notation from. Now if it's on the opposite side, so if r is greater than, so the absolute value is greater than 1 or equal to 1, then it diverges. It just goes away. Now 1 is going to be a redundant value because it's just going to keep adding. So it's like, if it's 1, it would be like 2 plus 2 plus 2 plus 2 plus 2 plus 2. But that keeps going on forever and ever anyway. So there's really, like, it heads to infinity. It doesn't converge to a certain number. So that's why it's included in that. So for the final example here, we want to be able to determine if the infinite geometric series is convergent or divergent. If it's convergent, we want to find the sum. Okay? So to see that, we need to figure out what the ratio is. And it's all based on the common ratio. So I need to divide one of these numbers by the other. So the second one divided by the first, so that gives me 1/3. If I want to do another one, 1/3 divided by 1 gives me 1/3. So it looks like my common ratio is 1/3. Doesn't change anything. R is less than 1 here, so this would be an example of it being convergent. So now I just need to find the sum of this. So our a value would be this 3 here that starts our sequence. So then 1 minus what r is, which is 1/3. So now I just need to simplify. So 1 minus 1/3 gets me 2/3. And then I want to multiply by the reciprocal to the top. So it gives me 3 over 1 times 3 halves, which gives me 9 halves. So that would be what this sum will converge to eventually once we hit infinity, would be 9 halves. Okay? Have fun.